Hello everyone, my name is Xiao and I am now working with Dr. Yi Bao and Dr. William Meng at Stevens Institute of Technology. Today my presentation topic is improving bridge resilience and sustainability through optimizing the high performance fiber reinforced cementitious composite. As we all know, compared with conventional concrete, HPFRCC can largely improve the mechanical performance of structures due to their superior material properties. However, HPFRCC is known to involve high material cost and carbon footprint, which may cause concerns in sustainability. One representative HPFRCC is UHPC. The price of commercial UHPC mixture in the US market ranges from about $2,000 to $3,000 per cubic meter, which is much higher than the conventional concrete. Besides, the high quantity of binders such as the cement in HPFRCC can have adverse impact on the sustainability. In fact, the cement is a product from the energy-intensive industry and also responsible for the large emission of the CO2 and global warmings. So based on this background, the overarching goal of this study is to develop a framework to improve bridge resilience and sustainability simultaneously by optimize the material designs of representative HPFRCC, including strain hardening cementitious composite SHCC and ultra high performance concrete UHPC. The content of this study, including the existing method for improving resilience, sustainability, and current challenges, proposed framework, results, and conclusions. Multiple solutions are proposed to reduce the cost and the carbon emission in HPFRCC. Materials experts develop cost-effective and eco-friendly mixture using the green raw materials such as industrial byproduct, solid waste, and recycled material. Structural engineers proposed only use HPFRCC at a critical position of structures such as the connection of bridge decks or the joints of buildings. However, the existing studies focus only on how material mixture design affect the material property of the HPFRCC, as marked in the green colors, or how the structural design use HPFRCC affects the structural behavior, as marked in the orange colors. However, it is still unclear how the use of HPFRCC will influence the resilience and the sustainability of structures. Usually using the supplementary materials in the mixture design benefits to the sustainability, but shows the negative effects on the mechanical behavior. There's a trade-off between the resilience and the sustainability. This brings another challenges, which is it is unknown how the mixture of HPFRCC should be designed to achieve the optimized resilience and the sustainability, as shown in the red colors. To address above challenges, this study is developed a framework using which has three specific objectives. First is to evaluate the resilience of bridges incorporating HPFRCC with different properties. The second is to develop an effective and efficient approach to enhance the material sustainability by optimizing the mixture design of HPFRCC. The third is to evaluate the effect of key mechanical properties of HPFRCC on the mechanical response of the bridges. In this study, the developed framework is performed based on the real collapsed bridge, machine learning, predictive model, and the failure element analysis, resilience and sustainability evaluations, and the multi-objective optimization is used to link the resilience and the sustainability of bridges with material design of HPFRCC. each subsections of the proposed framework will be introduced separately. The first subsection is a predictive model. We use auto-turn machine learning model developed by our groups, but due to the time limitation, the details is not introduced here. The predictive model are trained use a large quantity of experimental data of UHPC and SHCC. And this trained model was used to reflect the relationship between the mixture design variables and the mechanical properties of HPFRCC. The second part is the finite element analysis. It is performed based on the realistic collapse bridges with applying the string hardening model of the HPFRCC. We can get the relationship between the mechanical properties and the mechanical response of bridges. The third part is the resilience evaluations. In this section, resilience is defined as the ability of a bridge to maintain a level of performance during or after extreme events, and the ability to return to the desired performance level within the shortest time to minimize the impact to the communities as shown in these figures. The resilience value is calculated using the following equations, and the resilience classes can be determined based on these values. The resilience evaluation correlates the relationship between the mechanical response and the resilience. Based on the predictive model and the finite element analysis and the resilience evaluation, links can be established for the mixture design of HPFRCC and the material mechanical property, bridge response, and the bridge resilience. With these links, bridge resilience can be evaluated for a given set of mixture design of HPFRCC. Similarly, for a given set of mixture design of HPFRCC, the sustainability can be also evaluated. The relationship between the material cost and the carbon footprint and each raw integrate from the HPFRCC can be formulated using the following equations. Also, a sustainability index is proposed to rank the design solutions. The sustainability is between 0 to 1, 1 corresponding to the highest sustainability and 0 corresponding to the lowest sustainability. The sustainability evaluation correlates the mixture design of HPFRCC with the sustainability. With the links between the mixture design variables of HPFRCC and the bridge resilience and the sustainability, a multi-objective optimization is performed to achieve both high resilience and high sustainability at the same time. The bridge resilience here is said to be high as a constraint, and the optimized mixture design is searched to achieve the minimized material cost and carbon footprint. An intelligent algorithm is adopted to solve this problem and rank the design solution to get the highest values of the sustainability index. In this research, the developed framework is performed on a real collapsed bridges, and the finite element analysis and the resilience calculation is conducted to compare with the real situation of the bridges. According to the FEA results, we can see that the failure of the bridge is closely related to the tensile damage in the member 11 and its low-day regions. This is consistent with the real failure mode, and also according to the calculation result of the resilience values, this bridge is classified in the low resilience classes, so it's also aligned with the identified levels of damages. Then we compared with the mechanical response of member 11 of the bridge made by conventional concrete, SHCC, and UHPC. For the conventional concrete, the two joints of member 11 are severely damaged. However, for SHCC and UHPC, we can see that the damages is significantly reduced, and we only found minor damages in the member 11. We also investigated the effects of three material mechanical properties, including the first crack strength, ultimate tensile strength, and ultimate tensile strain. For the both SHCC and UHPC, the maximum tensile damage decreased with the variation of the material properties. And also we can see that the resilience value increased with the increasing of mechanical properties. This parametric result indicates that the use of UHPC and the SHCC is promising to decrease the tensile damage at the critical positions of the bridges, and therefore enhance the resistance to the collapse and also the resilience of the bridges. So when the bridge resilience is constrained to be high class to avoid collapse, a number of candidate solutions can be selected based on the optimization. This result in this slide shows that the mixture design of S1 is the most cost-effective and eco-friendly mixture with sustainability index about 0.89. So based on above investigations, we found that the presented framework can be used for enhancing the bridge resilience and sustainability simultaneously by optimizing the mixture design of HPFRCC. And the optimization of the mixture design enables HPFRCC to minimize the material cost and carbon footprint while retaining the high resilience of the bridges. And the tensile property of HPFRCC have a significant effects on the damage condition and the resilience of the bridges. The parametric study provides the data guide for the design of the structure using the HPFRCC. Finally, I'd like to introduce our groups. The newly established Smart Infrastructure Lab is aside the Hudson River and facing the midtown of Manhattan. This lab is used for large-scale structural testing, which is equipped with MTS high-capacity actuator and advanced instruments, such as optical cameras, fiber optic sensors. We also developed smart robots for the bridge condition assessment. We also have advanced concrete technology lab. We have 6 mixtures for mixing, universal testing machine, and environmental chambers for the mechanical, temperature, and humidity testing. We also equipped with the instrument for the multi-scale characterization of concrete, such as TGA MIP. We strongly welcome the research collaborations and educational opportunities. Thank you for listening, and please let me know if you have any questions.
I saw that you mainly focus on the mechanical property of the sample that you prepared. So I'm wondering, since you got a lot of durability testing class in your lab, do you have any plans of doing durability tests to see if your mixture maybe people feel more about this topic of resilience?
Sorry, I cannot hear you very clear because of the quality of this. I cannot get your
question. So I will make it quick. So for resilience part, you mainly focus on the mechanical property of your sample. And given to the introduction of your lab, you got many durability testing instruments. Do you have
Mhm.
any future plans to test your sample?
Yes, of course. We have the future plans for we have maybe not this large scale testing, but we can do some model testing in the lab to simulate these conditions and also validate our results.
And also you're gonna couple all these durability aspects into your model as
Yes,
well?
yes.
Okay, sure. Thank you.
Okay, thank you for your questions.
Do you have any other questions? Okay. Thank you, Mr. Jantan. Thank you very much.
Thank you.
One more time.